Engineering drawings and blueprints are a type of graphical language that communicates ideas and information from the engineer who designed a part to the workers who will make it. The graphical images in the field of the drawing are generated using a variety of line styles. Acceptable quality and consistency of the lines used to create blueprints is critical to accurately depict the final product. The lines described herein are merely conventions. Each drawing specification may have its own types and standards. Visible lines, sometimes called object lines, represent the edges or lines on an object. They are solid lines with a thick weight. Hidden lines consist of short dashes, evenly spaced. These lines are used to show the hidden features of a part. They begin with a dash in contact with the line from which they begin, except when such a dash would form a continuation of a full line. Center lines are composed of long and short dashes, alternately and evenly spaced, with a long dash at each end. Very short center lines may be unbroken if there is no confusion with other lines. On a front view, center lines cross without voids. A center line can also make the center of a hole on a side view. Hidden lines are used to show the extent the hole reaches into the part. Section lines are used to indicate the exposed surfaces of an object in a sectional view. They are generally thin, full lines, but may vary with the kind of material shown in section. Section lines are typically used when showing details of a part, where using hidden lines would be confusing. Section lines illustrate where material would be if the part were sectioned or cut, as if with a saw. Different patterns or direction of lines indicate different sections of the object. Dimension lines typically terminate in arrowheads at each end and include the dimension of the part within the line. They are unbroken except where space is required for the dimension. Extension lines are used to indicate the extension of a surface or to point to a location outside the part outline. They start with a short, visible gap from the outline of the part and are usually perpendicular to their associated dimension lines. They help illustrate how far a dimension extends. Leader lines are used to indicate a part or portion to which a number, note, or other reference applies and are typically unbroken lines terminating in an arrowhead. The most common use is when a dimension won't fit within the dimension line. Cutting plane lines are used to indicate a plane or planes in which a section is taken. The arrows at the end of the cutting plane line indicate the direction of the view or the direction your eyes look after the cut is taken. A viewing plane line is a line that indicates a special type of detail view. A viewing plane line is very similar to a cutting plane line, but it does not actually cut the part or generate a section. A viewing plane line is used when an interior view of the part is helpful in illustrating characteristics, but a full section view is not required. Break lines are used when a portion of the piece shows no useful information, and removing it is either convenient to save space or will allow further details to be illustrated. There are two types of break lines. Long break lines are typically full ruled lines with freehand zigzags that are used to show breaks in shafts, rods, tubes, rope, and so on, which have a portion of their length broken out for convenience. Short breaks are indicated by solid freehand lines and are typically used to illustrate smaller section views where removing material from the part illustrates features otherwise not shown. Phantom lines are composed of alternating one long and two short dashes, evenly spaced, with a long dash at each end. They are used in three ways. The first is to indicate the alternate position of moving parts. The second way phantom lines are used is to illustrate the position of related parts to better show how the part interfaces with existing or missing parts. Finally, phantom lines are used to show repeated detail. In this view, a spring is depicted. Since the coils of the spring are all the same, it's not necessary to draw them all. Instead, phantom lines are used to illustrate that the coils continue as originally shown. Electrons move around a nucleus of an atom in concentric orbits. These orbits or shells represent different energy states that electrons can exhibit. The farther an electron is from the nucleus, the greater its potential energy. While electrons typically remain in their prescribed orbital energy level, it's possible for an electron to be knocked from its lower orbit into a higher one. Thus, a bombarding free electron can collide with a bound electron, raising it to a higher orbit or energy level. This electron is now in a state of excitation. However, this higher orbital status is fleeting. The electron will be quickly drawn back toward the nucleus and return to its original orbit. During this transition back to its normal state, a single photon of visible light is emitted. This repeating sequence of electron excitation followed by de-excitation is the basis for the functional capacity of a fluorescent light bulb. A typical fluorescent bulb is filled with argon gas and a minuscule amount of vaporized mercury. The inner surface of the tube is coated with the powdery phosphor substance. At each end of the tube is an electrode with filaments. When heated to a high temperature, they emit or boil off electrons. An AC voltage pulse supplied by a starter pushes the electrons from one end of the tube to the other. If one of the free electrons collides with an electron of the mercury vapor, the electron is bumped from a lower to a higher energy level. The electron quickly returns to its lower energy state and in the process releases an ultraviolet photon. This photon is then absorbed by the electrons of the phosphor powder lining the tube, again exciting electrons in the process. This excitation is followed in turn by de-excitation and the release of a low-frequency photon. The photons from all these reactions combine to produce the glow of white light, characteristic of fluorescent bulbs.
Reading structural drawings is something that many students have difficulty with. I find it difficult to teach the topic because, as a structural engineer, it comes very natural to me. So, this video will provide a little insight into how I, as a structural engineer, go through a set of drawings. What we're looking at here is the first page of a set of structural drawings for a cultural center on the campus of Northern Arizona University. And I'm going to walk through the way that I look at this set of drawings. The first page here, you can see, starts with general notes. It's very common for structural drawings. And the first thing I do is page through the drawings just to see how things are organized and look for things that help me understand how the building is put together. So I start at the very largest level. I'll see the second page here. We can see that it's a set of typical details. Typical details are kind of boilerplate. They're nothing special. They're just the way many of the parts of the building are put together in similar fashion to other buildings. We'll see later a lot of specific details that were created just for this job. Another set of typical details. Usually the next thing we see are plans. So I open this one up and I can see a floor plan. We can see down here this is a foundation plan. The plans tend to go in sequence from the bottom up. What I find is very curious on this drawing is that there are no real dimensions showing me how to lay out the whole building. So right now I'm a little confused. I don't know how big this building is. I don't know really what's going on. I can see that it's probably a concrete foundation, but beyond that, it doesn't make a lot of sense to me quite yet. So I'm going to keep digging. I'm going to go to the next page here. You can see this says framing plan. So framing indicates that it's structural. So I might concentrate a lot down here on the titles of the pages. You can see right below here that these were issued for 100% construction documents, so I expect them to be complete. This has floor and low roof, so I'm looking at this saying, okay, some of these spaces here look like they're open, and some of them look like they might be floors, and some might be roofs. So I'm not quite sure what's going on. So let's go to the next page. Here's a high roof. Okay, so we've got a high roof and a low roof, and each of these lines is going to represent some sort of structural member. I'm not sure what the material is yet. I'm not sure if this is wood, if it's steel, if it's concrete. Not until I zoom in closely can I really tell that. Let's page to the next one. Now we're starting to get into the details. And typically structural drawings are organized in series, like 100s, 200s, 300s, etc. So here we can see the 300 series of the foundation details. That keeps that, the foundation contractor, organized in one spot. So I'm looking closely here, and as I start to page through here, I look and see that we have some typical details here with some concrete footings. So here we'll zoom in a little bit. We see a wall coming down on a little concrete stem wall, and then a little concrete footing. And typically on structural drawings, you'll get your how to build it in the details, but the dimensions will be on the plan. Also, for here, bottom of footing, see general structural notes. So these there's a lot of abbreviations that are used that we'll have to go back to the first page to get. But this tells us the detail of how to build it. Okay. I'm going to jump back out here. We'll go to the next page, and a couple more foundation details. Okay, so it's kind of a concrete, shallow foundation. I can see that we don't have deep drilled piers or caissons or anything, so that tells me a little bit about the building. Floor framing details. So now I look at this, I see a lot of things here that show how the walls and floors connect together. I'll just randomly pick one here. There's a detail. And what I'm seeing here are metal studs. So these are metal studs. I see concrete metal on a deck for the plan and a shelf angle here. So what I'm seeing are bearing walls built around the building and a floor that's built of metal deck with concrete on top of it. So that's generally the construction of this building. And you can see the details are all very similar. So these are just the different ways that the floors and beams connect to the walls. We'll go to the next page here. A couple more framing details. This looks like I got some ways that the stairs are connecting together. Now we get up to the roof framing details. So I see a lot of slants here, which tells me there's going to be some complexity to this job. Just zoom into one here. Again, we have metal studs, bearing walls, and then we have joists. So I'm not sure quite what these joists are. I see plywood. I'm guessing that these are probably wood joists, and we can see a slope to it. So now I'm seeing this complexity of the building, that we have a sloped roof going on. And I go to the next drawing and I see more roof framing details. So these are all details, and each one of these details will be called out somewhere in plan. So for instance, I'm right now on sheet S501, and this detail right here is detail number 9. So somewhere in the drawings there's going to be a call out for detail 9 on S501. The last one here, a few more roof framing details. So it looks like it's not too complicated. So the first thing I want to do is get a feel for what the building looks like. So I'm going to switch over to the architectural drawing. And as I page through the architectural drawings, we usually start at the bottom. So the first drawings typically have to do with the site plan. So here's a site plan. It shows how the building is going to be oriented relative, and looks like some demolition, so what was existing here, and how this new building kind of in this area is oriented relative to different roads. Looks like some landscaping going on outside. Here I see a dimension plan. This is not very common to have a dimension plan, but because I believe of the all the circular elements to this building, it's important to have the dimensions here. So right now I'm seeing, okay, because the dimensions are all shown here on the architectural dimension plans, the structural engineer decided not to show them to make sure there was no confusion. That way there's only one source for dimensions. So this is where, unfortunately, the structural contractors, the foundation contractors, are going to have to come here to lay out their building. I see a few things here. I see all these dimensions. I see this point of beginning. So basically this is the reference point for the whole building. Everything's referenced to that point. The circles here, the circle in the middle, and these curved walls are identified by center points right here. So you can see this one right here, control point number 2. And so if we go over here, center point number 2, you can see that there's some dimensions given, and these dimensions are measured from that point of beginning. So to start the whole building, the contractor is going to have to figure out where this point is from the civil drawings, and then everything is referenced off that. So now we know where everything is in this building. Here's the roof and mezzanine second floor dimension plan, and then we get into the architectural plans. So right now I can see, okay, this looks like we've got a gathering space, we've got some study rooms, and we have some offices around on the first floor. We go up to the mezzanine, and what I'm seeing in this X here shows an opening. This looks like line of roof, so there's a cutting through a roof here. These cut lines here indicate that we're slicing through it. That's probably the slope of our roof. And then over here it looks like we've got a stair going up, a little elevator shaft, and then these are the details I was talking about. So let's zoom right in here. So what we see here are some details. Now these are architectural details, but if we're looking for a blow up of the elevator, we have detail 2 on A500, and this little dashed line around the outside indicates that that's a blow up plan. These little details, and this symbol here shows elevations. So on A4.15, if we look at elevation number 4, it would be as if you were standing right here looking at that wall. Whereas if you were looking in this direction, you would see what you'd see in elevation number 5. So this gives me a feel for kind of how the building's laid out. I'm going to page to the next page here. This is where I see a roof plan, and what I'm seeing, if I zoom in here, are all these different slopes. So we can see that we have the roof sloping from an elevation of 26 to 23 to 22, and then this pops up. There's an elevator overrun here, so it pops up a little bit. So I see a valley. So I see a lot of complicated slopes here. So that's going to help me understand the structure by understanding the architecture. Let's see what else we can see from the architectural drawings here. If I jump to the elevations, we can see an elevation. So west elevation would be looking at the west side of the building. North elevation is looking at the north side of the building. So these are the directions that face west and north. And the architect has done a nice job of giving us an axonometric northwest. So this gives me a good feel. Okay, this building has curves and it has sloped roofs. There's that little elevator pop up where we're seeing punched windows. So I now have traversed the whole kind of set of drawings, and I have a feel for what's going on. It looked like back in this area by the elevator we had a little mezzanine. Otherwise, it's for the most part a single-story building. And that helps me understand the structure. So let's jump back to the structural drawings and take a little closer look. So I'm going to go back to the beginning, the general structural notes. And the general structural notes really give the detail about this type of building. There are specifications that will tell exactly how to build each part. However, the structural notes are different than most other trades where the specs take precedence. In structural drawings, typically it's the structural notes that take precedence over the specification. So let's jump in here, and by reading through the general notes, by skimming through them, we can get a good feel for a lot of the assumptions of this building and the materials. So let's just start off at the top here. I'm going to zoom into general. And first part is pretty much boilerplate. But as we move down, what we can see here is the building design criteria. So we know the building was done using the 2006 IBC. Typically on structural drawings, it's required to show all the loadings used for design. And this is because sometimes there's some items that are performance specified, such as curtain walls, that the contractors need to know what to design for. So this is all the information about the loads used in the building. Next thing we're going to go down to is see the soil bearing. So it should reference a soil investigation by who did it and the report number, and the minimum criteria for soil. So here it says that we have to put all the footings down 2'6" below adjacent finished floor or finished grade. So that keeps it below frost. Into engineered fill, there's the bearing capacity. So this tells me now if I'm going to build the footings, the shallowest I can go is 2.5 feet below grade. Materials and execution next. So we have concrete. We have concrete construction, and this tells me what the material properties should be for the concrete, aggregate size, etc. Most of this is pretty boilerplate, but this tells you where you notice that there's a difference. Unless otherwise noted, 4,000 psi concrete, but the fill on the metal deck is 3,000 psi. So that's good to know. Cast in place concrete gives us information about where the joint should be. Pretty standard. Reinforcing, this is standard. You really can't get any different types of steel. We'll go up to the next column. So a little bit more about the concrete and sandstone veneer notes. So I see, okay, there's going to be some structural sandstone. Looks like there's a fireplace going on. Then we have some structural steel. So we're mixing structural steel. We see ASTM designation. So this is the type of steel that's going to be used in the building. What to do about welding, what to do about bolting, minimum bolt sizes, adhesive anchors, headed studs, metal floor deck. So when they're buying the metal floor deck on the plans, it'll just say metal deck. Here it tells exactly how to install it. Structural steel framing. It says it's a non-self-supporting steel frame. That means the erector has to do some special things while erecting the building. Then we jump up here and we see cold formed steel. So now we have a different type of steel. The other steel that we're looking is what they call rolled steel or red iron. Different terms are used. Cold formed steel is basically sheet metal. It's metal studs and whatnot. So this particular building has a lot of metal studs and whatnot for the structural support. So you can see what materials are to be used, specifications for framing, and metal shear wall requirements. So there's shear walls made out of metal studs. Now I see the building has wood, so dimensional lumber, that's just 2x4s, 2x8s, etc. It has glue laminated beams, sheathing, which is basically plywood or OSB or something like that. Then we have shear walls on metal stud. We have plywood I-joists. Okay, so I see that those are like truss joists. So by going through the notes here, what I'm learning is the building is made up of a whole bunch of different materials. We've got wood, we've got metal studs, we've got concrete, And then we have structural steel. Let's jump up to the, and we see here that this is still with the wood I-joists, and then the lag screws and connectors, and a little bit of information about shop drawings. So how the shop drawings, so this is information that the contractor will need to know about submitting shop drawings and preparing shop drawings, special inspections that are required for this job. So there's the steel construction, the concrete construction, the plywood construction, and the soils. So there we have the general notes. And so by scanning through the general notes, I get a feel for what the materials are in the building, what the design parameters are, and what material specifications are needed for each one. The next thing I'm going to do is jump through the plans a little bit closer. So now I've already looked a little bit. I know that I'm going to have to go over to that architectural drawing to get my dimensions. But what I see here looks like we have some sort of bearing walls around the building, around the whole perimeter, sitting on concrete footings. And I'm seeing a lot of things here. Let's zoom into a corner and see what we can see. These little bubbles around things are revisions that were made with a little 1, so that ties it to something that was revised after the first issue of the drawing. Let's talk a little bit about lines on a foundation plan. When we have a dashed line, that indicates something that's beyond or hidden, like underneath the grade. So this line here is indicating these two lines are indicating the edge of the footing. You can see we have a square here, 3'6" square by 12" thick footing with 4 number 5 rebars each ways, typical of 3 places. Okay, so the engineer is getting a little lazy here. He pointed to one and says there's 3 of them. So I gotta go look somewhere else in the drawing. Looks like it's probably there's one and maybe that's the other one. Okay, so I'm assuming that those are made up the same way. What else do I see here? I see WF2. Well, WF, I'm thinking maybe is wall footing number 2. And so whenever we see a tag like this, usually indicates that the information is found in a schedule somewhere. So I'll have to go to a schedule to find out what WF2 means. Over here I have SW4 and it's pointing to the wall. So our thick lines here are things that we're cutting through. So what I'm seeing here is a thick line indicating the bearing walls. SW4 is probably a shear wall. And then these letters A, B, C, and D probably tell me something about the plan notes. Cutting over a little bit here. Here's one of these details. So I could go and let's look at this one right here. It's detail 1 on sheet S300. And it's cut right through here looking in this direction. So let's jump to that sheet and see what we can find. So here's sheet S300 and we need to find detail 1. So zoom into detail 1 here. And here's detail 1. And so what we see here is that wall footing. So from above, this was a dashed line and this was a dashed line here because this one's under soil and this one's underneath the slab. We had 3 lines on the top. Let me jump back and show you those 3 lines. So right here we've got the 2 dashed lines and then the 3 lines. So and it's the same, I think we were looking at this detail. So we have two lines widely spaced and 1 close by. So when we jump back to detail 1 on S300, what we're going to see is these 2 lines indicate the top of the wall, and that's a little bit of a ledge. Okay, like I said, when we were looking down, this was the outside line, and these were the 2 top lines. So what we were looking down, we were cutting through the wall, and we were seeing this little bit of a ledge. The dashed line here indicates that it's the architectural exterior wall. And then here's the indication of the metal studs. 800S16254 just talks about the size of the stud. It's an 8-inch stud, the 1.62-inch flange on it, and then that has to do with the gauge of the stud. We space them 16-inch on center, unless otherwise noted. And this tells us a little track to put down, and then the specifications and notes will tell how to fasten them together. On structural concrete drawings, these heavy lines indicate rebar. The size of the hooks are usually not shown because those are standard per ACI specs. So a standard 90-degree hook is what the contractor would give there unless there's a dimension shown. A circle indicates a rebar that we're cutting through, so those are longitudinal ones. So you can see in this wall, you can see this line here. The contractor would come in and build the footing first with these pieces of rebar. And then these are called dowels that would stick out of that footing, and they come back and build the wall. So they'd form up the wall, put these rebar in it, and then they'd come back, do the slab, do the insulation, do the backfill, build the wall on top. So we build from the bottom up. Here it says see plan for size and reinforcement. So if we jump back to that plan, we'll know how to reinforce this particular one. So let's do that now. So we were looking at S300. So let's jump into this little area here. This tells me it's wall footing number 2 is running along here. So I'd have to find a schedule with wall footing number 2 on it. And what I see over here is the wall footing schedule. So let's jump over here. So wall footing 2, 2 feet wide, 12 inches thick. It has 2 number 5 bars continuous. Continuous means they put the bars in and they have to put lap splices, and again the distance in the lap splice will be told by the drawings, by the specifications. And then here it says typical unless noted otherwise. So if there's a footing that's not labeled on the drawing, the contractor knows use this one unless it's noted with one of these other indications. So now I have a good feel. There are little strip footings around the perimeter. Remember from the general notes they had to be 2'6" below the exterior grade or the finished slab. In this case the exterior grade was lower. So that tells the contractor how deep to go. You'll note on the drawings it didn't give any elevations, which puts a lot on the contractor to figure out. So we got those footings. We have these little spread footings here. Let's zoom into the middle and see what's going on. So I see this. I see this one here is looks like a footing. Here it's called out, a 4-foot square by 12-inch thick footing with 4 number 5s, each way typical of 4 places. Okay, so there's 1 of them, there's 2 of them, there's 3 of them, there's 4 of them. Here's a detail cutting through 1 of them, again on detail 3 on S300. And these round things are steel pipes. Again, there's no dimensions shown here, which is actually curious. We typically would show the dimensions on a structural plan, but this architect and engineer decided to show all the dimensions elsewhere. So the contractor is going to have to do a lot of work to figure out where these go. It's a 6-inch diameter, extra strong pipe column with a 3/4 inch square base plate, 4 J-bolts typical of 4 places. So we have 4 steel columns going up here, holding up probably the roof. We could jump over to S300 again and see what that detail looks like. Let's go to that detail 3 on S300. And this is what we just saw in plan. Talked about the footing. So that was the one we saw, the 4-foot by 4-foot plan. It gave the reinforcement in the plan. Here's our anchor bolts. It's reiterating what it said in plan, but it gives us our embed distance now. A little bit of how to actually build it, some dry pack grout. Typically on structural columns, we put the footing down at least a foot. On this drawing, it doesn't quite show where to put it. So we'd have to go back to the plan to see the elevation. But we put the footings down lower so that we can bury the base plate below the slab. Then the slab comes right and nice and neat up to the column. You have the column here. Detail 4 looks down at the base plate, so it shows how to lay the anchor bolts out. So let's go look at detail 4. Presume it's down here a little bit. So there's detail 4 looking down. We have the pipe column. This is a weld symbol showing how to weld the pipe to the plate. Here's our 4 anchor bolts, 1.25 inches from the edge. So I think I have enough information to build that column. So let's jump back out to the plan. So as an engineer trying to figure out the building, I would be going through all this, and I'd just go through it on a careful basis just to try to figure things out. So let's jump up to the framing plan and see what we have. I'm looking here, and what I'm seeing, let's take a zoom into this corner. What I'm seeing here is symbols for beams. So this is W10 by 12, which is an indication of a steel beam. It's a W shape, 10 inches deep, that weighs 12 pounds per foot. These are all details on the sheet 400 on how to connect things together. This is a little symbol showing how to build the floor. So when we show steel, we typically don't show the concrete. So it's as if you're looking through the concrete and you see the steel beams. We can see which beams support which beams by the gaps. So for instance, the first thing they would build is the column. Then this 10 by 26 would come in. They'd build the exterior wall, and then the 10 by 12s would frame across. So the gaps indicate where the different beams end. Over here, it's an indication of what the metal deck looks like. So it's almost like we've peeled away all the deck from everywhere and left a little piece of deck just to indicate that the deck spans this direction, and then concrete will be poured on top. Here's a note. It's 2.5 inches of normal weight concrete with some welded wire mesh fabric over 1.5 inch type B 22 gauge deck. 2.5 plus 1.5 gives a total structural thickness of 4. So we'll be laying that in. And so all these details pretty much show how everything comes together. I can see that this is a stair that goes down. We've got details exactly how to connect all the pieces of the stairs together. So this is a little area. It's a concrete and steel framed little mezzanine. Let's pan around a little bit. Let's go over here. Now what I'm seeing here, tongue and grid plywood per structural notes on 11 7/8 TJIs. So TJIs, we'd have to go back to the notes, but a TJI is a plywood I-beam. So now we have wood construction over here. So you can see, again, it's kind of cut away, but I see AHU1 3,300 pounds. So this looks like it's supporting an air handling unit. Double joist. So there's a little wood mezzanine. I walk around here. I see SL2. Well, I know that these are walls, so I'm thinking that's probably a steel lintel, and I'll find a schedule somewhere that talks about SL2s, and it should be titled steel lintels. Here we have 600S 162 ceiling joists. So that tells me that these are metal studs by the designation. So we have a 14 by 22. We have some more ceiling joists over here. We have a little pipe column. 2-span continuous steel lintel. Rolled. Rolled means it's curved, so they actually bend the piece of steel around the radius. Again, around the radius. Go over here. Looks like we have some more metal stud joists. And tongue and groove over some 11, almost 12-inch TJIs. So this just looks like a little mezzanine plan here. So we got a bunch of different construction materials. We've got rolled structural steel with metal deck and concrete. We have wood TJIs or truss joists with plywood, and we have metal studs, and we have steel lintels. Okay, we'll jump over here. We'll look at these floor framing notes. It's always good to read the notes. A lot of good information there. So if we look at this, this tells us kind of where to go to get some information. Down here denotes steel header at openings. So L for lintel or header. So it just tells you what detail to go to. So a lot of times your general notes are going to cover very basic things that look like they're missing from the drawings. And we'll jump up to the roof here, and let's scan through the roof. And again, we're not going to figure out the whole drawing here, the whole building here, but we get a general feel for what's going on. So let's again start up in this corner here. These little arrow call outs tell us what the how to make connections, I'm guessing, and these are little details of how to make other connections. So I see 11 7/8 wood truss joists in this area being supported on a W21 by 50 steel beam, if we scan around here, we've got some roof area is plywood sheathing. And right here we have truss joists at 24 inch on center. Here we have a steel beam going across, is 21 by 50. C 3/4 inch means there's a 3/4 inch camber on the beam. It looks like this little symbol here looks like it stops, so it's a 21 by 44, runs over the column, and then there's a splice and another splice there, and then we have these 3/8 inch by 13.5 inch glue laminated beams going between here. So I'm looking at this, I know this is kind of a great room. I'm thinking, okay, architecturally they wanted to expose some wood on the underside. We could go to the architect's drawings to confirm that. So if we remember what we saw from the three-dimensional drawing, so this is what the building looked like. We have these different structural roofs. We've got this roof that goes around that's sloping this way, and then we've got this part that pops up that slopes this way. Looks like a little skylight and a little elevator shaft. And so by looking at that, I can see, okay, we've got all these different framing systems going on. So you can see this is an elevator shaft, here's a little skylight, this is one roof sloping like this, and then we have this perimeter roof going around. So really there's a lot going on here. What I thought was useful by doing this little exercise is just to walk you through my thought process as a structural engineer when I go through a set of drawings, the things I look for and the things I go through. Thank you.
Process calibrators are used by technicians to measure and calibrate sensors and transmitters. Using an RTD, or resistance temperature detector, as an example, the initial step of calibration is verifying the accuracy of the temperature sensing device. To perform the measurement, the process calibrator is programmed to the specific RTD type. The accuracy is determined by measuring the temperature of water at 0 degrees Celsius and 100 degrees Celsius, representing freezing and boiling points of water. Connecting the RTD output to the calibrator, the measured temperature is displayed using the measure function. After the sensor accuracy is confirmed, the next step is verifying the accuracy of the transmitter using the process calibrator. The calibrator provides an input signal to the transmitter that simulates the output of the sensor at multiple measurement points. With a transmitter range of 4 to 20 milliamps, the expected output at the low end of the temperature range of 0 degrees Celsius is 4 milliamps. At the high end of the temperature range of 100 degrees Celsius, the expected output of the transmitter is 20 milliamps. Calibration is performed by using the zero and span adjustments to tune the appropriate current value for the simulated temperature. The copper atom has 29 positively charged protons and an equal number of electrons in various shells orbiting its nucleus. After filling the first shell with 2 electrons, the second with 8, the third shell with its maximum 18 electrons, the outermost shell of copper is occupied by a single electron. The lone electron is loosely held in its valence orbit and thus can become a free electron. The ability of this electron to freely move away from its nucleus gives the copper atom its current carrying capacity. Let's take a more detailed look at how these free electrons flow when a voltage is applied across a copper wire. Taking a simplified version of a copper atom with its single valence electron, let's distribute copper atoms along the length of a copper wire. In the absence of a voltage, the free electrons in a copper wire will drift in random directions from the orbit of one atom to another. When a voltage is introduced to the copper wire, the electrons can be directed through the wire, with the electrons moving towards the positive end of the source voltage. This movement or flow of electrons in one direction is called electron current flow, or just current. Materials that have free electrons and allow electrical current to flow easily are called conductors. Conductors, such as copper, have low resistance to electrical current flow and thus are used extensively in electrical circuits. A functioning motor has three basic settings: resting, starting, and running under a load. The running of a motor creates heat. For the most part, this heat buildup is harmless, but if the heat reaches high levels, the motor's sensitive functional components are at risk. When a motor is drawing too much current and creating excessive amounts of heat, it is called running in overload. If a motor runs in overload for any length of time, the excessive heat can damage the motor. To protect motors from running in overload, manufacturers typically protect their products with an overload relay connected to the motor starter. When an overload relay trips, it opens contacts within the control circuit, stopping the motor. The most common type of overload relay uses a melting eutectic alloy. A eutectic alloy is a specific type of metal that changes directly from a solid to a liquid at a fixed temperature. In a melting alloy overload relay, the eutectic alloy is housed in a tube along with an inner shaft cemented in place. This tube is connected to a ratchet wheel. The temperature of the alloy is controlled by a heater coil wrapped around the outside of the tube. The heater coil is directly connected to the circuitry of the motor, so when dangerous amounts of current run through the motor, the wire coil will also heat up. When the heater coil gets hot enough to melt the inner eutectic alloy, it indicates that the motor has reached a dangerous overload threshold. At the elevated temperature, the alloy will instantly turn from a solid to a liquid, allowing the inner ratchet shaft to turn freely. When the wheel turns, it releases a pawl previously engaged in one of the cogs of the ratchet wheel. This pawl is connected to a spring-loaded contact fixture, such that when the pawl trips, the contacts automatically open and stops the current flowing to the motor starter. The spring-loaded contact fixture also includes a reset button so that when the eutectic alloy cools and cements the ratchet in place, the contacts can be closed by re-engaging the pawl in a cog and compressing the spring. Another important part of motor electronics is forward and reverse circuitry. Here is an example of the circuitry for a forward and reverse three-phase motor. When the motor is running in forward, the circuitry contacts are connected in numerical sequence: L1 to T1, L2 to T2, and L3 to T3. To run the motor in reverse, then, two of the contacts must be switched. In this case, L1 is connected to T3 and L3 is connected to T1. L2 and T2 remain connected. This reversal of contacts will cause the motor to run in the opposite direction. Great care must be taken with forward and reverse circuitry because if the forward and reverse contacts ever engage at the same time, it will cause a destructive and dangerous short circuit. In order to protect against this kind of short circuit, manufacturers employ three types of interlocking safety systems. Interlocks create a web of safety checks within a circuit to prevent both forward and reverse coils from being energized at the same time. They are represented in circuitry diagrams by a dotted line. The most basic level of interlocking systems is a mechanical interlock. A mechanical interlock is a physical lock that prevents the forward and reverse contactors from being engaged at the same time. The second level of protection is an electrical interlock. An electrical interlock works by using normally closed auxiliary contacts within the opposite circuitry, so that when the forward button is pushed, there is a check to make sure no current is running through the reverse circuitry. The same is true when the reverse button is pushed. The final level of protection is the push-button interlock. This interlocking system works by physically opening the button contact within the opposing circuit. This way, if for some reason both buttons get pushed, then no current will flow at all. The purpose of fluid power is to transmit power from one location to another. In the mid-1600s, Blaise Pascal, a French mathematician, made a very important contribution in the field of fluid motion. This contribution, known as Pascal's law, relates the transfer of pressure through a fluid. Pascal determined that a contained pressurized fluid will exert pressure equally in all directions. Pascal's law states that pressure set up in a confined body of fluid acts equally in all directions and always at right angles to the containing surfaces. Another important property of fluid mechanics was discovered in the late 1600s by Robert Boyle, an Irish physicist. Boyle's law is an experimental gas law which describes how the pressure of a gas increases as the volume of gas decreases. A modern statement of Boyle's law is the absolute pressure of a confined body of gas varies inversely as its volume, provided its temperature remains constant. In a physical system, this means that as the volume decreases, the pressure increases. Similarly, as the volume increases, the pressure decreases. Boyle's law can be expressed mathematically as the pressure at state 1 times the volume at state 1 is equal to the pressure at state 2 times the volume at state 2. This is true as long as both the temperature and mass, or amount of gas, remains constant. In the late 1700s, Jacques Charles, a French scientist and mathematician, discovered an important rule regarding gases under pressure. Charles's law, also known as the law of volumes, is an experimental gas law which describes how gases tend to expand when heated. It states that if the pressure of a gas is constant and its temperature is raised, the volume will also be raised by the same ratio. Additionally, the inverse is true. If the pressure of a gas is constant and the temperature is lowered, the volume will also lower. Charles's law can be expressed mathematically as the ratio of the temperature at state 1 to the volume at state 1 is equal to the ratio of the temperature at state 2 to the volume at state 2. This law is true as long as the pressure and mass remain constant. In the mid-1700s, Daniele Bernoulli discovered another very powerful rule in the field of fluid mechanics, known as Bernoulli's principle. This rule is related to the theory of conservation of energy, which states that energy can neither be created or destroyed. In this fluid system, pressure is potential energy and fluid flow is kinetic energy. Bernoulli's principle states that an increase in the speed of an incompressible fluid occurs simultaneously with a decrease in pressure. This is illustrated by the flow of water through a pipe. The volume of water flow through all three sections is the same. When the water's flow is restricted in section B, the speed of the water increases to maintain the same amount of volumetric flow. This increase of speed simultaneously causes a decrease in pressure. When the flow of water reaches section C, the inverse occurs. The water flow decreases and the pressure increases. This rule can also apply to the types of energy present in the system. As the pressure decreases in section B, the potential energy converts into kinetic energy. This increases the speed of water flow and decreases the pressure. When the water reaches section C, the kinetic energy is converted back to potential energy. This is illustrated by the decrease in speed of the water flow and its simultaneous increase in pressure. The purpose of an inductor is to oppose any change in the magnitude of current within a circuit. The electrical property that resists either an increase or decrease in current is known as inductance. An inductor is created when an electrical current flows in a wire wrapped around a magnetic core. You may recognize this as an electromagnet represented by flux lines that develop around the core with the formation of a north and south pole at their respective ends. To demonstrate the properties of an inductor, we'll add a resistance or light bulb to this circuit. As the switch is closed and the current flows through the circuit, the electromagnetic field in the inductor forms and expands rapidly. However, because of the unique properties of an inductor, as the flux lines of the electromagnetic field expands, the changing current generates a voltage that resists the current coming from the source. The maximum opposition to current flow occurs at the instant the switch is closed. Therefore, the bulb will not turn on instantaneously. However, once the electromagnetic field stops expanding based on the level of changing current, the flux will no longer generate an opposing voltage in the circuit. The current will continue to flow and reach its maximum value after 5 time constants, or 5t, where t is equal to L divided by R. The light bulb will then be at its maximum brightness. If you open the switch and stop the flow of current from the source, the electromagnetic field will diminish rapidly and simultaneously release stored energy in the form of voltage. It will actually generate enough voltage to cause a spark across the switch as it opens. Whereas a capacitor uses voltage to store energy, the inductor uses current. Inductance of an inductor is defined as the amount of voltage induced, divided by the change in current per second. Therefore, if 1V is induced by a change of 1A in 1 second, there is 1 Henry, 1H, of inductance. Control valves are valves used to control conditions such as flow, pressure, temperature, and liquid level by fully or partially opening or closing. Traditional control valves are the most basic type. The flow control of a traditional control valve is typically limited to fully open, fully closed, or fully switched to a new flow path. Traditional control valves are of simple design and capability. Changing direction, flow, or pressure during machine operation would require a complex hydraulic circuit. Each desired direction, flow, or pressure would require an individual traditional valve to control it. Proportional control valves offer a solution to the complexity dilemma without introducing dozens of valves and hydraulic loops to the system. Physically, proportional valves appear similar to their on-off solenoid counterparts. The big difference is in the way their solenoid coils perform. Proportional coils operate on DC current and produce varying voltages that in turn produces a variable force to shift the spool. The graphic symbol for this type of solenoid shows the solenoid slash in the operator box with a sloping arrow through the slash. With proportional valves, the spool can be shifted against the centering spring force to any distance up to full shift by varying voltage and current. As the internal valve spool changes position, new flow areas open up gradually and continue to open wider during full spool travel. To eliminate flow lag from spool overlap, most manufacturers cut V-notches that allow some flow to pass as soon as the spool moves. Proportional control valves allow for variable control of spool movement, which allows more step control and metering of flow, speed, and direction. Most valves of this design are used in open-loop systems to smoothly accelerate and/or decelerate an actuator or cylinder. The proportional control valve allows for a simpler hydraulic circuit, but it is not accurate over a broad range of pressures, flows, and temperatures. Neither are they highly responsive. Proportional valves offer a variety of machine cycles, which can safely be operated at greater speeds and result in improved machine cycle times and production rates. The third type of hydraulic directional control technology is called the servo valve. First developed in the 1940s, the servo valves operate with very high accuracy, repeatability, and high-frequency response. Servo valves are highly responsive and capable of handling minuscule flow changes both rapidly and accurately over a broad range of flow rates, but at an extra cost. The main difference between proportional and servo valve circuit design is that servo systems have a method of feedback that assures that the actuator is doing what the controller tells it to do. Most industrial applications use feedback from electronic linear, rotary, or force transducers. A transducer is a device that produces an electrical signal in direct relation to a position, force, or speed. These devices feed a precise position or speed indication back to an electronic controller via a feedback wire, which in turn adjusts the valve. Fluid from the pump inlet is tapped off through filter elements, passes through orifices past both ends of the spool, goes on to nozzles, and out to the return line. A feedback wire attached to the flapper terminates in a ball end that sits in a very close-fit slot in the spool. When the torque motor coils receive a current signal, the armature rotates clockwise or counterclockwise and pushes the flapper closer to one nozzle and farther away from the opposite one. This allows pressure to increase at one end of the spool and decrease at the other. The spool then starts to move away from the higher pressure. If the armature turns clockwise, pressure builds on the left end of the spool and it moves to the right. With these very accurate feedback devices and a fast response servo valve, an actuator's position, speed, and/or force can be repeatedly established within an extremely close range. Electronics provides the accuracy while hydraulics provides the force via a super responsive servo valve. Proper evaluation of the requirements for a particular application can assist a technician with evaluating the performance of a valve and its suitability for the task at hand. The function of a closed-loop system is to monitor and automatically maintain a variable at a desired set point in a manufacturing process. Using an example of a heat exchanger, the operation of a closed-loop system is compared with a block diagram. The heat exchanger supplies heated water to a food processing operation. Cold water enters the bottom of the vessel where the water temperature rises as it passes through steam-heated coils before flowing out of the pump at the top. Each block represents a function of the operation. Lines connecting the blocks indicate input and output signals of each function, with directional arrows indicating the process flow. The controlled variable is the actual variable maintained in the process. In this example, the controlled variable is the temperature of the water leaving the tank. Measured variable monitors the status of the controlled variable. Water temperature is the measured variable in the process. The measurement device senses the measured variable and produces an output signal that represents the status of the controlled variable. The thermal sensor that measures the water temperature in the heat exchanger is the measurement device. The sensor provides an electrical signal to the controller and is defined as the feedback signal in the block diagram. Set point is the predetermined value of the desired condition of the control variable. In the heat exchanger, the set point is the programmed value of the water temperature leaving the tank. Error detector compares the set point to the feedback signal and produces an output proportional to the difference between them. Error signal is the output of the error detector. If the feedback signal and set point are equal, the error signal is 0. The controller is the brain of the system. It receives an error signal as it inputs and provides an output signal to the final control element or actuator in this example. A signal from the controller causes the controlled variable to match the set point using the actuator of the system. The flow valve represents the actuator where steam flow is controlled. The amount of energy or steam in this example, altered by the actuator, is the manipulated variable. Manufacturing process is the operation of the heat exchanger to control the physical variable. Disturbance is defined as a change in the manufacturing process resulting in a change in the control variable. Disturbances occur when the water temperature suddenly changes or stops flowing. Closed-loop control and the associated terminology are common within manufacturing systems where precise control is required. In most air and hydraulic fluid power circuits, valves are used to control the direction, rate, and pressure in fluid lines. Control valves for these functions can be purchased with either manual or solenoid actuators. In a manually actuated valve, the internal cylinder is shifted by hand using a lever, push button, plunger, or other manual actuating device. By contrast, valves with a solenoid actuator respond to an electrical signal for shifting. With electrical control, machine cycles can be set up for automatic sequencing, and operator control can be exercised from a remote location. Solenoid valves are said to be either direct or pilot operated. A direct operated valve is shown here. A pilot operated valve has a pilot and bleed orifice and utilizes line pressure for operation. This is a pilot-operated relief valve. When the solenoid is energized, the core opens the pilot orifice and relieves pressure from the top of the valve piston or diaphragm to the outlet side of the valve. This results in an unbalanced pressure, lifting the piston or diaphragm off the main orifice. When the solenoid is de-energized, the pilot orifice is closed and full line pressure is applied to the top of the piston or diaphragm, closing the valve. Most directly operated valves also come in pilot-operated versions and are designated by a triangular graphic symbol. A single solenoid valve has one solenoid to assist in valve operation. The valve spool shifts when the solenoid receives an electrical signal and is energized. The valve will remain shifted as long as electrical current is applied to the solenoid. Once the electrical current is removed and the solenoid is de-energized, the valve returns to its normal position by spring force. Fluid circuits designed to use single solenoid valves must maintain electrical current in order to keep the valve in its shifted position. Double solenoid valves have two solenoids, typically mounted on opposite ends of the valve body. This type of two-position double solenoid valve does not have a spring return. When the first solenoid is energized, the valve spool shifts into the first position. Even if the first solenoid is de-energized, the spool remains shifted. This is because there is no spring to return the spool to its original position. Energizing the second solenoid will send the valve to the second position. Even if the second solenoid is de-energized, the valve will remain shifted until the first solenoid is re-energized. Since there is nothing holding the valve in the shifted position other than friction, these types of valves should be mounted horizontally to avoid self-shift due to excessive airflow or vibration. If both solenoids are energized at the same time, the solenoids will work against each other and may cause the spool to become stuck, electrical burnout of the solenoid, or an overload of inrush current to the circuit, any of which will cause severe damage to the system or valve. A three-position valve has a spring-centered neutral position for its internal spool. Because of the centering springs, it's necessary to hold current on one solenoid or the other to keep the spool in one of its side positions. When each solenoid is energized, the valve shifts to the appropriate position. Anytime both solenoids are de-energized, the valve spool will spring to center and stop the fluid flow. Therefore, a three-position valve requires a maintained electrical signal for its operation. As before, energizing both solenoids at once may cause damage to the valve or to the system. To prevent this from occurring, electrical circuits should be designed to make it impossible to have current on both solenoids at the same time. Solenoid valves are used in both hydraulic fluid and air systems to control direction on cylinders from deceleration or speed control and pump unloading or pressure control. The physical appearance of each component will vary greatly depending on brand, size, and type, so care should be taken to reference the appropriate manufacturer's guidance when choosing a solenoid valve. Transformers are composed of an iron core ring wrapped in coils. One coil is connected to an AC input voltage and is called the primary coil. The other coil is connected to an output circuit with a load resistance and is called the secondary coil. The two coils are well insulated from each other and do not form a physical electrical connection. This gives a transformer its unique electricity-altering properties. Transformers can either step up or step down a voltage. In a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. The constantly changing current driven by an alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage at the load or resistance in the secondary circuit. If there are fewer coil turns on the secondary than on the primary, this is called a step-down transformer. The resulting voltage in the secondary circuit will be less than the primary. In this example, we have 20 turns on the primary coil and 10 turns on the secondary coil. To determine the decrease in voltage occurring in this step-down transformer, we can use a simple ratio formula. This formula simply states that the secondary voltage to primary voltage ratio is the same as the secondary coil to primary coil turn ratio. Rearranging the formula and then dividing 10 turns by 20 turns, we get 0.5 multiplied by 120V. This results in a calculated step-down voltage of 60 volts. The term fluid motor is normally used to identify those devices which deliver continuous rotary power output when supplied with fluid under pressure. The term motor is sometimes used by manufacturers to denote reciprocating cylinders. Technically, this is a correct usage but can lead to a misunderstanding of the type of actuator to be used. For the remainder of this video, we'll use the term motor to describe a continuous rotating device. Whether to use a cylinder or fluid motor depends upon its application and the type of load to be moved. At first glance, it may seem that cylinders are the better choice. For applications where either can be used, a cylinder is typically less costly compared with a fluid motor of the same horsepower. Cylinders have leak-tight, non-metallic piston seals, which will give a consistent performance at very slow speeds against a wide range of load resistance. Fluid motors, on the other hand, have metal-to-metal internal surfaces which use a small amount of leakage for lubrication purposes. A cylinder with leak-tight seals can be operated over a wide range of speed, under changing loads, and with reasonably consistent performance. A fluid motor can only perform similarly if it's designed with precision tolerances to reduce its natural internal leakage, which increases cost. Cylinders also produce smaller pressure spikes, called hydraulic shock, when stopped suddenly. Fluid motors tend to produce a much larger amount of hydraulic shock if stopped suddenly due to the momentum energy contained in their rapidly rotating loads. Finally, cylinders are much more efficient than the typical fluid motor. Energy loss can be held to about 5% in a well-constructed cylinder, but fluid motors or pumps experience power losses from fluid leakage and friction within the device. These losses can be anywhere from 10 to 25% of the input power. However, despite all of these setbacks, fluid motors are advantageous due to their complete rotary motion and the ease with which their speed and direction can be controlled. On most fluid motor applications, it's necessary to have a motor which can accept high pressure on either port so that the motor can be reversed. In all hydraulic devices, a small part of the high-pressure oil will slip through clearances between the gear sides and the housing and will collect in the seal and bearing pockets. If not vented, these pockets would soon be exposed to the same high fluid pressure as the ports, which can then dislodge the shaft seal. To prevent this from happening, several motor construction methods are used. The first method creates an external case or housing drain. The seal and bearing cavities are internally joined and vented through a drain port. Another method to prevent fluid buildup uses internal check valves. These valves allow accumulated leakage to flow in a specific direction to either main port, but will prevent backflow of high pressure into the bearing and seal pockets around the shaft. Finally, high-pressure shaft seals are utilized to minimize the consequences of high-pressure fluid exposure. These are mechanical seals in which two lapped surfaces run against each other to seal the shaft. A rotating surface, called a seal ring and typically made out of bronze or graphite, is pressed against a stationary surface called an insert, which is typically made out of steel. A spring ensures that the seal ring presses tightly against the insert. A packing, or O-ring, ensures there is no leakage between the spring and seal ring. Internal hydraulic pressure ensures the two surfaces are held in tight contact, but even this method is not leak-tight, and weepage is a common occurrence. Additionally, the lapped surfaces are sensitive to contaminants in the oil, which are abrasive and cause leakage to increase. Fluid motors have many advantages over typical electric motors. An electric motor can be prone to overheating, especially if it experiences higher than normal loads. Fluid motors, on the other hand, will simply stall and come to a stop if they are overloaded. Once the motor stops, the fluid begins to cool down. Additionally, unlike an electrical motor, fluid motor speed can be made responsive to its fluid temperature. If a sensor detects an increase in fluid temperature, the speed of the motor can be directed to reduce. Due to their advantages, fluid motors can be the ideal choice for conveyors, hydraulic transmissions, fan drives, vehicle drives, cable reeling or winching, and many other industrial applications. Capacitors work to store energy by stretching the orbits of electrons in a dielectric compound between a positively charged plate and a negatively charged plate. As charge accumulates on the positive plate, the electrons of the dielectric material gravitate toward the positive plate, distorting their orbits. The attraction of the nucleus to the negatively charged plate further stretches the atoms. This process of distorting the orbit of the electrons uses energy that then becomes stored in the dielectric material. A capacitor must be attached to a closed circuit with an energy source, such as a battery, in order for it to store energy. When the switch is closed, electrons flow and charge builds up on the capacitor's plates. This causes the voltage across the capacitor to increase. Eventually, the voltage across the capacitor will equal the voltage of the sources. At this point, the flow of electrons stops because the source voltage and capacitor voltage is equal but opposing each other. The capacitor is essentially charged. All capacitors charge at the same percentage rate. Based on the universal charge curve, after one time constant, the capacitor will have reached 63.2% of its potential, 86.5% after two time constants, and so on. After 5 time constants, the capacitor has reached 99.3% of its potential and is considered essentially charged. A time constant in seconds is equal to the resistance of the circuit in ohms multiplied by the value of the capacitance in farads. For example, in this circuit, if you have a 1 megaohm resistor and 5 microfarads capacitor, the time constant would be 5 seconds. Therefore, for each 5 seconds of elapsed time, the capacitor will achieve its corresponding voltage percentage until it reaches an effective charge after 5 time constants. A rotary actuator is an output device for a fluid power system that delivers an oscillating motion over a limited range of less than one full revolution of a circle. A true rotary actuator produces work by direct action of fluid pressure against internal vanes. Work is defined as a force applied over a distance. Rotary actuators produce a special type of rotational work called torque. Torque occurs when a force acts on a radius. Since rotary actuators operate at low speed with high torque, torque output rather than the horsepower is used for the rating and identification purposes. Speed is a secondary consideration when choosing a rotary actuator for a particular application. The typical units of measurement for torque are foot-pounds. For example, if a rotary actuator with an arm length or radius of 2 feet were used to lift a 200-pound weight, then the resultant torque required to accomplish the work would be 400 foot-pounds. Due to the way in which it is calculated, there are an infinite number of possible system configurations that would also yield a torque equal to 400 foot-pounds. In this example, torque is easy to calculate because the lever arm is at right angles to the force exerted on the arm. However, when the angle between the force and the arm changes to something other than 90 degrees, an additional calculation becomes necessary. When the lever arm moves, the length of the arm can no longer be used as the radius of the system. Instead, the effective radius must be determined. To calculate the effective radius, multiply the length of the lever arm times the sine of angle A. Sine is a trigonometric function for a right triangle that relates the ratio of the side opposite of a given angle to its hypotenuse. Sine has values that vary from 0 to 1 for angles between 0 and 90 degrees. When the lever arm is in the vertical position, the angle between the rope and lever arm is 0. The sine of angle 0 is also 0. Therefore, when the lever arm is vertical, the torque will be equal to 0. As an angle increases, the sine also increases, which will increase the torque. When the lever arm is at right angles to the force of the weight, the angle is equal to 90 degrees. The sine of 90 degrees is equal to 1. It is at this angle that the torque is at its maximum value for the system. Understanding the relationship between the output torque required and the physical setup of a fluid system enables designers to determine the appropriate rotary actuator for each unique application. Absolute encoders are used in many applications that require speed, position, angular displacement, and directional feedback. An encoder is a device that converts linear or rotary movement into digital or pulse signals. The most common type of feedback device is the absolute optical encoder. An absolute encoder consists of the 4 major components: a rotating encoder disc, a light source such as an LED, a photodetector as the light sensor, and a signal conditioner that converts the signals into square waveform. The encoder disc consists of a series of opaque and transparent tracks mounted to a rotating shaft. The tracks of the disc are arranged concentrically around the center of the shaft. Photodetectors assigned to each track designate the resolution of the encoder. The higher the number of concentric tracks, the higher the accuracy. A light source located on the opposite side of the photocells passes light through a capture plate. As the encoder disc rotates, light is either transmitted or blocked according to the pattern. The received light provides a 4-bit word that indicates position of the actuator or device the encoder is mounted to. The most common types of numerical encoding are decimal, binary, and gray code. In a 4-bit encoder, there are 16 unique combinations or numeric code every 22.5 degrees. Gray code is designed where only one bit changes at a time, contrary to a binary system where one or more numbers change in the word. By changing more than one number of the word at a time in the binary system, the possibility of positioning errors is greater, leaving gray code the preference in precision applications. For robot applications, absolute encoders are commonly used for precise positioning operations. The actuator in this example demonstrates the function of the absolute encoder in operation. As the actuator moves to push the carton, the encoder provides feedback that it has reached the user-defined position. The actuator then moves back to the home position, verified by the encoder, and completing the cycle. Using feedback devices closes the loop in motion control systems. A DC drive is the functional circuitry that can be employed to precisely control a DC motor. The drive operation allows the application of varying DC input levels so that the motor runs efficiently at different speeds. A DC drive circuit is composed of 3 main components: an operator controller, a drive controller, and a DC motor. One of the functions an operator controller provides is a method for altering the speed of the motor. The drive controller will regulate the input by means of either a phase control device or a pulse width modulator. And the DC motor can be an electrical device that needs to be adjusted to perform at various speeds. Let's look at the phase control method in a bit more detail. Phase control works by modulating a gated diode-like device, such as a silicon-controlled rectifier or SCR, into and out of conduction at a predetermined phase of a rectified AC half wave. This diagram depicts an AC sinusoidal wave being altered by a full-wave rectifier to produce partial half waves. The partial half-wave output produced is reduced based on when the firing device is activated. Adjusting the speed at the operator controller will determine when the SCR is activated and at what point in the half-wave cycle the wave is turned on or allowed to pass through. The area of the waveform will determine the amount of voltage delivered to the motor. Pulse width modulation, or PWM, is a method that uses digital signals to control power applications. In this example, a PWM uses a full-wave rectifier to convert an AC input voltage into a DC output level of 300 volts. A control circuit operating a DC switch turns the DC output on and off. This controller device can be an SCR or a powerful transistor. The on and off cycling of the controller circuit produces a repeating 300-volt square wave with a fixed frequency and width, as illustrated by this typical output displayed on an oscilloscope. One of the parameters of a square wave is the duty cycle. This is derived by dividing the time on duration or width, t sub 0, by the duration of the wave period, t. Thus, if the period is 2 milliseconds and the time on duration is 1 millisecond, then the duty cycle is 0.5. The voltage reduction will be 0.5 times 100% or 50%. Multiplying the duty cycle times the input voltage will give you the voltage output. In this example, a 300-volt input will be modulated by 50%, so the final voltage delivered to the load or motor is 150 volts. Thus, controlling the speed of a motor can be achieved by modulating the square signal waveform. Ever wonder why normally heavy objects seem to weigh less underwater? It's due to the buoyancy. Even a heavy metal weight becomes lighter due to the buoyancy properties of water. When an object is submerged into a liquid, a buoyant force is simultaneously pushing it upward. When an object is buoyed up, its apparent weight is equal to its actual weight, minus the weight of the liquid that it has displaced. This relationship is known as the Archimedes principle. Archimedes' principle was discovered by Archimedes of Syracuse in the 3rd century BC when he sat in the bathtub and noticed the water rising around him. The principle states that the upward buoyant force exerted on any object submerged in a liquid is equal to the weight of the fluid that it displaces. If we submerge a 25 kilogram weight and it displaces 20 kilograms of water, then its apparent weight underwater is 5 kilograms, the original weight minus the weight of the displaced water. So the next time your friend is hoping to impress you with his feats of strength lifting a large weight while underwater, explain to him the Archimedes principle and the buoyant properties of water. Vacuums have a widespread use of commercial applications, including its use in welding applications, vacuum pumps, plastic molding, aerospace flight instrumentation, semiconductors, medical equipment, and finish and coating applications. A vacuum can be thought of as negative air pressure. Atmospheric pressure is defined as the weight of the atmosphere, or air, exerted on the Earth's surface and is typically measured with a barometer. At sea level, all of the weight of the atmosphere above is pressing on the Earth. Therefore, the atmospheric pressure is at its highest. As elevation increases, the total amount of atmosphere directly above the surface is much less than at sea level. Therefore, the atmospheric pressure is much lower. Atmospheric pressure decreases as elevation increases. The maximum force available from a vacuum is dependent on the barometric pressure at its location. At sea level, the barometric pressure is about 14.7 pounds per square inch under standard conditions. A vacuum can be thought of as negative air pressure and is measured with any set of force per area units. In the customary U.S. system of units, atmospheric pressure and vacuum pump force are measured in inches of mercury, abbreviated Hg, which is the atomic symbol of mercury. Determination of this measurement is made with the use of a mercury barometer. Mercury barometers are made with a long tube closed on the top end, open at the bottom, and immersed in a pool of mercury. The tube is then raised to a standing position without allowing air inside. The mercury level falls until a balance is reached between the weight of the mercury in the column and the atmospheric pressure against the surface of the mercury pool. With this method, the empty space at the top of the tube forms a perfect vacuum. At sea level, the elevation of mercury will stand at about 29.9 inches of mercury. As the atmospheric pressure decreases, the height of the mercury in the tube decreases. As the atmospheric pressure increases, the height of the mercury in the tube increases. If a vacuum pump is connected to the top of the mercury column and allowed to run, the mercury column would not rise as high as with a sealed barometer. This is because no vacuum pump can achieve a perfect vacuum. Vacuum pumps are given their rating based on how high they can pull the level of mercury upward towards a perfect vacuum. Vacuum technology has developed significantly over the past few decades. Vacuum packing is used in a variety of industries to package and protect products. Plastic forming is also a widespread use of vacuum technology. In this application, a sheet of plastic is heated until it is malleable. Then a mold is applied and a vacuum is used to form the plastic to the mold. Additionally, vacuum chucking is a commonly used method to hold workpieces in place without the risk of damaging their surface. In this application, a piece of wood is held to a lathe so that it can be turned. New applications for the use of vacuum power will continue to grow as technology advances. Water, like any substance, is made up of molecules. The mobility of these molecules is determined by temperature. When heat is added to water, the vibration of its molecules increases, causing the water to expand. As the water molecules vibrate faster, they bounce around, pushing each other away, causing the space between them to increase. This graph shows how the volume of water expands as its temperature increases from 4 degrees Celsius to 18 degrees Celsius. Here is a graph showing the increase of water volume over a larger range of temperatures. However, there is an important anomaly that should be noted. When you zoom in on the graph between 0 and 4 degrees Celsius, you'll notice that there is no expansion in this range. In fact, there's a slight decrease in volume. This is due to water's unique property of having less density as a solid than as a liquid. This can be explained by the crystalline structure of ice. When water molecules cool down, they vibrate less. As the temperature reaches freezing, these slow-moving molecules latch onto each other at specific points, creating rigid ice crystals with a distinctive lattice shape. The relatively large space between frozen water molecules is the reason that ice is more voluminous than water and likewise less dense. As ice is heated from 0 to 4 degrees Celsius, it begins to thaw. However, because melting is not an instantaneous process, the water molecules transforming from the crystalline state to a liquid are decreasing in overall volume, while the water molecules absorbing heat in the liquid form are increasingly more active, which increases volume. However, because the collapse of ice crystals dominates these two opposing processes, the net effect is a decrease in the overall volume. Once the water reaches 4 degrees Celsius, however, expansion takes over as most of the ice crystals have melted and the freely vibrating water molecules can move about with increasing mobility. Various numbering systems use symbols to refer to a number of items. Our common decimal system uses 10 numeric symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Sometimes called the base 10 system. We use this system to write numbers and perform mathematical operations. The position of a digit in the base 10 system determines its magnitude. This is referred to as place value. Moving from right to left, we multiply each preceding digit position by 10. Therefore, starting from the right, the first digit position is 1. The second digit position is 10 times the first, or 10. The third digit position is 10 times the second, or 100, and so on. The magnitude of the numbers 6, 9, and 4 is determined by the position of the digits. With the 6 in the third position, we would multiply 6 by 100 to derive its place value of 600, then add to it 9 times 10, or 90, and to that 4 times 1 to get 694. The binary system also uses place value to determine the magnitude of a number, but uses only 0 and 1 as numeric symbols. Thus, it is referred to as the base 2 system, with each position incremented by a multiple of 2. Digital systems use the base 2 system for computational operations in many of its applications. Now let's consider place value in the base 2 system. Starting at the right, we have 2 to the 0 power, then 2 to the first power, then 2 to the second power, and so on. Thus, each multiplier to the left is 2 times the preceding number. Thus, starting with position 1, we have 2 to the 0 power, or 1. Position 2 is 2 to the first power, or 2. Position 3 is 2 to the second power, or 4, and so on. When you work with digital equipment, converting between the binary and decimal numbering systems is often required. Let's take the binary number 110101 and convert it to a decimal number equivalent. We will add together all the decimal number place values converted from a binary string. Thus, moving from right to left, we encounter a 1. Multiply it by its binary place value of 1 to give 1. Considering the next position to the left, we have a 0. No decimal numbers are derived when zeros are encountered because 0 times its multiplier is 0. The next binary number is 1. 1 times 4 is 4, so we include its place value of 4. We do this conversion for each place value of the binary number. Thus, adding up all the decimal numbers gives 53. Now, let's apply a process for converting a decimal number to its binary equivalent. This method involves repeated divisions by 2. Taking the base 10, number 37, and dividing by 2, we get a quotient of 18 with a remainder of 1. This remainder occupies the first position. Next, you'll divide 18 by 2 to get the next digit. It will be 9 with a remainder of 0, so 0 will occupy the second position. Moving along, the third position will be determined by dividing 9 by 2. This will give you 4 with a remainder of 1 to occupy the third position. Applying this divide by 2 process to each new calculated quotient derives the remainders that become the zeros or ones used to create the binary string. Continuing until the quotient is 0 and can no longer be divided by 2 completes the conversion process, and you have your binary number. Atoms make up all of the Earth's matter. Atoms can be broken down into 3 basic components: positively charged protons, negatively charged electrons, and neutrally charged neutrons. The number of these components and their arrangement determines the atom's elemental properties. Here we have a helium atom. Helium atoms consist of 2 protons, 2 neutrons, and 2 electrons. The nucleus at the center of the atom is made up of protons and neutrons. The nucleus is relatively small in relationship to the rest of the atom. In fact, if an atom were the size of a football stadium, the nucleus would only be as big as a pea. The remainder of the atom's volume is made up of shells with electrons orbiting around the nucleus. While the electrons orbiting the nucleus occupy a relatively vast amount of space and comprise most of an atom's volume, they have virtually zero mass. Protons and neutrons, on the other hand, although very small, contribute most of the mass of an atom. Electrons are arranged in the electron cloud by the distance of their orbit from the nucleus. These orbital layers are also referred to as shells. Each shell can hold only a certain number of electrons. The exact number of possible electrons per shell is defined by a rule of quantum mechanics stating that each orbit is filled when its electron count equals 2 times n squared, or 2n squared, where n is the number of shells away from the nucleus for which you are calculating the maximum number of electrons, also known as the principal quantum number. To calculate the number of electrons in the first shell, you would use the equation 2 times 1 squared, which is 2 times 1, or 2 electrons. For the second shell, it would be 2 times 2 squared, or 2 times 4, to give 8 electrons. For the third, 2 times 3 squared, or 2 times 9, equals 18 electrons. And for the fourth shell, it would be 2 times 4 squared, or 2 times 16, yielding 32 electrons, and so on. Elements may have up to 7 shells. Though each shell may not have its full allotment of electrons, this formula can be used to calculate the theoretical electron capacity for elements having a maximum of 7 shells. Fluids used in mechanical systems come in many different types. The type of fluid chosen for a particular application depends on its characteristics. One of the most important characteristics of a fluid is its viscosity. Viscosity is defined as a fluid's resistance to flow. Fluids with low viscosity flow very easily. Water is a type of fluid with low viscosity. Fluids with high viscosity are more resistant to flow. Honey is a type of fluid with a high viscosity. Therefore, honey is more viscous than water. Another characteristic of fluids is the viscosity index. This rating relates the flow of a fluid with its temperature. Many fluids begin to flow more easily as temperature increases. The viscosity index is the measurement of this characteristic. A high viscosity index indicates a small oil viscosity change with temperature. A low viscosity index indicates a large oil viscosity change with temperature. Compressibility is another characteristic of fluids. It measures the change in volume of a fluid as a response to a change in pressure. Fluids, such as gases, are highly compressible. Their volumes change significantly when placed under pressure. Liquid fluids also have a compressibility factor. Water and petroleum-based hydraulic fluid are almost completely incompressible. They don't compress when put under pressure. This characteristic is what allows them to be used to transmit power in fluid systems. Years ago, water was used as the first hydraulic fluid because there was no other liquid available in such large quantities at such a low cost. There are some major drawbacks to using water as a working fluid. Due to its low viscosity, it is difficult to pump. Additionally, the speed at which it flows through the system causes an effect known as wire drawing. Wire drawing occurs when the water flow erodes or scores a pathway in the metal of machinery as it goes around corners and through orifices. It also has corrosive effects on metal machinery. Over time, petroleum-based hydraulic fluids have become much more cost-effective. For starters, it has a lower specific gravity than any other liquid and can be pumped with less power loss. It also lubricates as it works through the system and has little corrosive effects on metal machinery. Flammability is an issue, but with the development of synthetic oils, alternatives to water remain the preferred working fluid. Several factors should be considered when designing a fluid system that uses a petroleum-based hydraulic fluid. The first is cleanliness. Oil never wears out, but it can become so contaminated that it is unfit for further use. Fluid systems frequently employ filters throughout the system to help reduce contaminants. They may also require complete fluid replacement after certain time intervals, and this can become cost prohibitive with larger systems. Another factor common to hydraulic fluids are the use of additives. Additives can be used to reduce aeration and the production of bubbles as the fluid travels rapidly throughout the system. They can be used to administer corrosion inhibitors within the reservoir, and they can be used as a demulsifying agent, which helps the fluid resist mixing with water. The choice of modern fluids is so wide that when designing a new system, fluid characteristics such as viscosity index, cleanliness, filtration, and additives should be considered as early as possible in the design process. Light is an electromagnetic wave that transports its energy at a speed of 300,000 kilometers per second. This constant speed is how fast light travels in a vacuum and is referred to as the speed of light, or c. When light encounters a medium such as air, water, or glass, it propagates through the substance at a net speed that is less than c. This slowing down of light through transparent objects is a form of energy transport that involves the absorption and re-emission of the light wave energy by the atoms of the substance. Imagine that the electrons in an atom are attached to the nucleus by springs. The elasticity of these imaginary springs will determine how much the atom vibrates when acted upon by an incoming particle of light energy. When light impinges upon the atoms of a material, its energy is absorbed. This absorption of energy causes the electrons within the atoms to undergo subtle temporary vibrations. This transient vibrational action is transmitted from one atom to another until it emerges from the other side of the material at the same light wave frequency and speed. While these vibrations are only short-lived within each atom, overall these actions delay the transmission of the wave energy through the medium. Thus, while a light wave travels at a speed of 300,000 kilometers per second through a vacuum, or the gaps between atoms, the absorption and re-emission process in different materials results in the net speed of the light wave to be less than the speed of light. In water, light travels at about 75% of its speed in a vacuum, or 225,000 kilometers per second. In glass, light travels at 67% of its speed in a vacuum, so the light speed is 300,000 times 0.67, or about 200,000 kilometers per second. Light travels very slowly through a diamond at about 41% of the speed of light, or 125,000 kilometers per second, which is less than half the speed of light in a vacuum. A silicon-controlled rectifier, or SCR, is a specialized type of control diode. The electron flow is the same as in an ordinary diode, from cathode to anode. However, unlike other diodes, which only perform an on and off function, a SCR can regulate a flow of electricity with gradation when forward biased. This is accomplished by manipulation of the adjustable gate control. This gate control function determines when and how much the SCR conducts. A common application of SCRs is in light bulb dimmers. Here is a circuit that contains a light bulb and a SCR. As the switch at the gate controller is adjusted to control power in the AC circuit, note the timing of the gate pulse and the subsequent change in the waveforms. Also, observe that average current flow increases and the light bulb becomes brighter. Analytical measurement and control of pH within a system is necessary for many processes. Common applications include food processing, wastewater treatment, and chemical industries. To maintain the desired pH level in a solution, a sensor is used to measure the pH value. If the pH is not at the desired set point, a reagent is applied to the solution. When a high alkaline level is detected in the solution, an acid is added to decrease the pH level. When a low alkaline level is detected in the solution, a base is added to increase the pH level. In both cases, the corrective ingredients are called reagents. Accurately applying the correct amount of reagent to an acid or base solution can be challenging due to the logarithmic characteristics of pH reaction in a solution. Implementing a closed-loop control system maintains the pH level within a certain range and minimizes the degree to which the solution becomes acidic or alkaline. An example of an automatic pH level control system is a water treatment process where lime-softened water is maintained at a pH of 9 using carbon dioxide as a reagent. As the untreated water or influent enters the tank, the pH is continuously monitored by the pH sensor. The sensor is the feedback device to the controller where the set point is compared to the control value. If the values are not equal, the controller sends a signal to the control valve that applies carbon dioxide to the tank. The reagent is applied to the tank at varying rates to precisely control the pH level. With the pH level at 11 detected by the sensor, the controller commands the control valve to open and introduce more carbon dioxide. As the increased carbon dioxide mixes with the influent, the pH is lowered in a controlled manner. Reaching the set point, the carbon dioxide flow is minimized and the process is continually monitored for variation. The effluent is the treated water that is discharged out of the tank. The process continues to provide the lime-softened water at the desired pH level. All matter is made up of atoms. At the center of the atom is the nucleus, which contains positively charged protons. Also found in the nucleus are neutrons, which have no charge. Orbiting the nucleus are the negatively charged electrons. Electrons are held in orbit around the nucleus because their negative charge is attracted to the positive charge of the protons. Here, we have a helium atom with its 2 electrons traveling in 3-dimensional orbits in the first energy level or shell of the helium atom. The nucleus is made up of 2 protons and 2 neutrons. The number of electrons and protons of an atom is always the same. Now let's look at a 2-dimensional representation of an aluminum atom. Aluminum has 13 protons and 14 neutrons in its nucleus. 13 electrons occupy various orbits or shells around the nucleus. The 2 electrons nearest the nucleus occupy the first shell. The first shell can contain only 2 electrons. Unlike the helium atom with its single shell around the nucleus, the aluminum atom will need additional shells to accommodate its additional electrons. Thus, the second shell will accept its limit of 8 electrons, with the third or outermost shell containing the remaining 3 electrons. The outermost shell of an atom is called its valence orbit. The electrons in this shell are called valence electrons. Valence electrons are responsible for giving certain atoms, such as copper, their important current-carrying electrical properties. The farther electrons are from the nucleus, the weaker their attraction to the nucleus. In the case of the copper atom, after the third shell is filled with its maximum 18 electrons, the remaining electron occupies the outermost fourth shell. This single electron is loosely held in its valence shell and thus is able to temporarily break away from the atom and become a free electron. When a valence electron leaves an atom to become a free electron, it takes with it the negative charge. The result is a net positive charge for the copper atom. This atom with one less electron than its normal number is called a positive ion. When the atom has an extra electron beyond its normal state, it is called a negative ion. To further investigate how negative and positive ions are formed, let's look at the compound sodium chloride or table salt. Sodium chloride consists of a sodium and a chlorine atom. Sodium has 11 protons and an equal number of electrons. Chlorine has 17 protons with the corresponding 17 electrons in orbits around the nucleus. Each atom is looking to become more stable. Sodium by giving up its single loosely held electron in its outer shell, and chlorine by gaining an electron to increase its outer shell number to 8. Thus, when salt is dissolved in water, sodium will readily give up its loosely held valence electron to chlorine, making both atoms more stable. With its one less electron, sodium becomes a positive ion, and chlorine, with the addition of an electron, becomes a negative ion. The positive ionic state of sodium and the negative ionic state of chlorine results in the atoms being attracted to each other. This attraction forms an ionic bond that holds the two atoms closely together to create a sodium chloride molecule. The properties of ions allow certain materials to possess current carrying capacity found in many electrical devices. Piping and instrumentation diagrams provide information that include component identification, how instruments are connected, where instruments are located, and their function within a process. Comprehension of P and ID diagrams assists technicians when troubleshooting and monitoring specific processes. Comparing a heat exchanger to the piping and instrumentation diagram illustrates the symbol's function within a process. Steam is conveyed through a pipe into a sealed enclosure that acts as a heat exchanger. As the water passes through the heat exchanger, the temperature of the water is elevated. To read the control loop, a series of steps are performed. Identification of the control loop is notated by the tag number 401 within the balloons. The valve that allows steam to flow through the pipe is the symbol with two triangles. In the top portion of the symbols is the functional identifier, and the first letter denotes the measured variable. The first letter of each functional identifier is the letter T, which defines the process of temperature control. The instrument connected to the heat exchanger contains two other types of information. The second letter in the functional identifier indicates it is a transmitter, and the balloon with no line inside its symbol indicates the device is field-mounted. A capillary tube that sends a signal from the heat exchanger to the transmitter is represented in the diagram by the line with X's. A dashed line between components indicates an electrical signal. The controller and indicator is the instrument where the transmitter sends an electrical signal and is shown in the functional identifier at the second and third letters, I and C. Balloons with a solid dividing line indicates that the instrument is board-mounted. An electronic signal from the controller is indicated by the dashed line. The controller output is connected to the transducer that controls the steam flow, indicated by the second letter Y of the functional identifier. The transducer converts an electronic signal to a pressure signal and is indicated by the square containing the letters I and P. The line with diagonal marks designates a pneumatic connection. The pneumatic-controlled diaphragm actuator that opens and closes the globe valve regulates steam in the process. The actuator is represented by the half circle in the P and ID. The arrow pointing downwards from the actuator indicates a fail-closed valve type. Many different types of pumps exist to assist fluid movement in a variety of systems. An external gear pump uses two gears rotating against each other to provide fluid movement. One gear is driven by a motor connected to a shaft. This is called the drive gear because it is driven by a motor, and it in turn meshes with and drives the movement of the second gear. As the gears rotate away from each other and come out of mesh, they create an expanding volume on the inlet side of the pump. This creates a vacuum at the inlet port, allowing fluid to flow into the pump. Then fluid flows into the cavities and is trapped by the gear teeth. As the gears rotate, a flow path is created around the outside of each one. Fluid trapped in the slots between teeth is carried around and discharged into the cavity with the outlet port. Meshing of the teeth in the center of the pump seals the outlet port from the inlet port. No fluid passes between the gears. The advantages of external gear pumps are their high speed and pressure, relatively quiet operation, and that their design accommodates a wide variety of materials. Disadvantages include bushings in the liquid area can become worn and that they have fixed end clearances. Internal gear pumps are exceptionally versatile. This type of pump has one inner gear which is inside a second outer gear. The inner gear has a shaft driven by a motor and has teeth that protrude outward. The outer gear has teeth that protrude inward toward the center of the pump. As the inner gear rotates, it meshes with and moves the outer gear. Liquid is trapped in the gear spaces and carried from the inlet to the discharge. A stationary crescent-shaped divider separates the intake and discharge portions of the fluid. Advantages of internal gear pumps are a smooth and almost pulseless flow, and slightly more horsepower for its size. Disadvantages are its higher cost, limited size range, low to moderate pressure ratings, and few sources of manufacture. A rotary vane pump is a positive displacement pump that consists of vanes mounted to a rotor. The vanes are on an off-center drive shaft. As the shaft rotates, the variable length vanes slide in and out to maintain contact with the pump housing. The tension in the vanes is maintained by either springs or hydraulic pressure. As the vanes rotate, they create chambers of varying sizes within the pump. Fluid enters at the largest chamber. As the vanes rotate and retract, the chambers get smaller, forcing fluid to exit through the discharge port. The advantages of vane pumps are that they can handle low viscosity fluids at relatively higher pressures, can dry run for short periods, and develop a good vacuum. Their disadvantages include complexity and their unsuitability for both high pressure and high viscosity fluids. Piston pumps come in many different forms. A swash plate is a device used to translate the motion of a rotate shaft into the reciprocating motion of a piston. Swash plate piston pumps have a rotating shaft connected to a cylinder block containing pistons, which are pressed against a stationary swash plate that sits at an angle to the cylinder. As the shaft rotates, the pistons move against the swash plate, causing them to reciprocate within the piston block. The pistons create a vacuum that forces fluid in during half a revolution and expels fluid during the other half. On the intake stroke, a spring ensures the pistons pull back and maintain contact with the swash plate, causing fluid to fill the empty cavity left behind. On the discharge stroke, the angle of the swash plate forces the pistons back inside the piston block and discharges the fluid. The greater the slant on the swash plate, the further the pump pistons move and the more fluid they transfer. Piston pumps, in general, are manufactured with closer internal fits than other pumps. This means that internal slippage can be less so that they operate with reasonable efficiency at pressures both too high or too low for the operation of other pumps. Radial pumps are designed so the pistons stroke in a direction at right angles to the shaft. The pistons are arranged like wheel spokes around a cylinder block with an eccentric central cam mounted on a drive shaft. As the shaft rotates, the cam moves towards the pistons, forcing them down into the cylinder block and discharging the fluid. As the cam moves away, springs help retract the piston and cause the intake stroke. Check valves ensure that fluid only enters the inlet ports and only exits the outlet ports. Radial piston pumps have a low noise level, very high loads at low speeds, and high efficiency. Hand pumps are used when a source of power is not available or where the extra expense of a power pump isn't warranted. For example, they are used on shop presses and other portable equipment, serve as standby pumps, and serve as sources of emergency power. Hand pumps are always of piston type and are usually constructed with a piston working between two check valves. Double-acting hand pumps are more efficient, allowing fluid to both enter and discharge on both strokes of the piston. Moving the pump handle in either direction allows fluid to be drawn in from the reservoir and discharged via the outlet ports. Check valves in all locations prevent fluid backflow.